positions particle staying on the teeth of the column are positions that mean something physically. In between, it just is ill-defined. The system hops from one state to the next. You can in fact fill in the distance between the columns. You always divide delta t by 2 and say, well, my system is in transition from one state to the next, and I call that a new state. And so you have some physical freedom in defining what delta t is. It's a very small number, and it's not obvious to me whether it's a well-defined number even. But these are details that can only be explained more precisely if you have a much more concrete model. In the case of neutrinos, of course, delta t is infinitesimal.
So in a sense, you don't have anything like Lorentz invariant. You don't have a space of defined in the way.
The neutrinos are Lorentz invariant.
You try to reproduce it in the Lorentz invariant way at the end of the day.
Sorry?
You try to reproduce it in the Lorentz invariant way.
Yeah, so neutrinos, they by construction are Lorentz invariant. So it's not impossible to build in Lorentz invariant. But I have to add immediately that making them interact is very, very difficult. I don't really know how to do that correctly. So, and then very likely you're going to blow up Lorentz invariance. So, how Lorentz invariance re-enters into nature is still something of a mystery.
And yet another question is, if I understood, you paid special attention about the polarization states of the spin-1 particle, which is smooth. But for any massless particles, it is generic that only two polarization states can exist for the physical state, right?
Okay, these particles, the particles have one polarization, the antiparticles have the opposite polarization. So these are chiral neutrinos.
Yeah, but not only for spin 1 and half it happens, but if you take spin 1, it also physical states are always along or opposite.
Yeah, I can ask, I haven't really tried to repeat this for photons or other things, because in the case of fermions, you understand it at that level as having holes and particles. If you have bosons, you have an integer on the slots, running from minus infinity to plus infinity. That's higher. So I'm a bit hesitant to introduce bosons at this level.
Further questions? Please.
Well, I'm here.
Also,
Okay. So as I can see, this picture of action of your evolution operator is periodic, right?
so say that again.
The action of your evolution operator is periodic. Look at the circle.
Yes.
Then, at some point, when you reach, now I see that another picture on the right, when you reach state with maximal energy, you go and you reach energy zero. Or if you interpret as particles and antiparticles, your particle will evolve into antiparticle.
No, sorry. I have to distinguish I'm not sure I understand the question. You have to distinguish the energy states and the position states of the particle. So I start with the position state. So my original model had just things hop like that. But then the energy is not well defined. So the particle in position space, the energy is not well defined. The energy is defined by diagonalizing the evolution operator or the Hamiltonian operator. So before diagonalizing that, the energy is not well defined. You get the well defined energy by superimposing all these states. Right? And then you have this, or it'll mark down now, there was this operator which links me from the position states to the energy states. In the energy states, Hamiltonian is diagonal, not in the position states. So these do not have well-defined energies.
Yeah, because I have fear that there is some sort of UV-IR mixing in this construction.
Sorry,
There is some sort of ultraviolet infrared mixing in this construction.
Well, it's a little bit at a too primitive level here.
Yeah.
But you are right that if you take the continuum limit, you have an ultraviolet and an infrared problem, and they talk to each other. Yes.
Okay, that's what I was mentioning. And I think it is due to non-locality.
Sorry?
This is due to non-locality in this construction.
Normal?
Non-locality. It's non-local. Non-local.
Non-locality?
Yeah.
Yeah. Well, the way I phrase that is you see the non-locality here in the sun. The sun goes all the way to infinity, and 1 over n is too slowly converging. So the very, very large time steps enter into the definition of the Hamiltonian, which was supposed to describe only infinitesimal time steps. The Hamiltonian describes infinitesimal time steps, but you need very, very large time steps to define the Hamiltonian. The large time steps move a particle very far away from where it was. So that's why this Hamiltonian is not quite as local as I might want it to be.
Okay, thanks. Yeah.
Other questions?
Okay, I can ask also, I think it's sufficient.
What people sometimes complain that
Oh, okay. No, I'm trying to figure out, of course, this is a very idealized system, this neutrino, non-interacting, etc. But if we try to think of a measurement process in which, as seems from, if I understood well from your recent papers, the measurement is represented by variable. So how they match this? Because in any case, I mean, the particle, let's say here, the object is, has some no locality. So I'm a bit puzzled about this. I mean,
Well, in the second quantized description, locality seems to be very well preserved. So in the second quantized system, my Hamiltonian little h is local, and the Hamiltonian is very much like a Dirac Hamiltonian. So at this level, I've restored locality. I don't know whether you think that the Dirac Hamiltonian is local or not. Right? But basically, this operator annihilates and this operator creates a neutrino basically at the same point, only epsilon away from each other because it's a derivative component h, but still at practically the same spot. So for all practical purposes, this Hamiltonian is local. So I restored locality by applying the Dirac trick.
no, this is okay. I mean, my point is about the measurement process. Because,
But,
because you see, then if that is represented
Maybe
by
I have
variable, then I have a problem to connect this with that level. I mean, I don't understand
I'll
simply.
discuss measurement and such things after the break.
Okay.
So maybe I'm sure you have questions because I only have about half an hour to discuss everything, and I'm sure there will be questions left, but maybe we can discuss that.
so we can have a break now.